Thank you. You guys can hear me all right? So the revolutionizing word, by the way, is a nod to the revolutionary aerospace, aerosciences 2030. But some of the things we are doing are pretty revolutionary. I've been around long enough to see that. First, let me start by making some comments about exactly what's happening in simulation these days. So I'm at a company now called Cadence Design Systems. How many here have heard of Cadence? Right? How many have heard of Cadence 5 years ago? It's actually a company that is one of the leaders in EDA, electronic design automation. But what's happening is there's a hyperconvergence of disciplines going on between mechanical and electrical. And some of the more traditionally mechanical disciplines are being stood up at these traditionally EDA companies. And computational fluid dynamics is one of those technologies. At Cadence, we think about three cross-cutting aspects of technology that support all of the simulation products that go on. In the middle is computational software. That's the software you use to do simulation. We call it principled simulation, simulation based on principles. At the bottom, there's a cross-cutting layer based on computational hardware. So that's the acceleration layer. And then at the top is AI. Really, it's optimization, orchestration, data. So our CEO at Cadence likes to call this a three-layer cake. Now, a cake isn't exactly that exciting, but the reason he calls it a three-layer cake is because when you slice a cake in any way, you slice it vertically. And so every representation of our simulation software gets all three layers. The layer I'm going to tell you about, or the slice of three layers I'm going to tell you about today, is our CFD layer. So in CFD at Cadence, there have been a number of acquisitions over the last 7 years, and there have been a number of internal organic developments, and we're bringing them all together into CFD products that have these four driving areas as their focus. And they all start with A. My youngest son has been trying to get into college lately, and so A is really resonant in our family these days, and so I thought, yeah, 4 A's. Who doesn't want that? The 4 A's we're talking about here are automation, acceleration, accuracy, and AI enablement. So on the automation side, that's automation not just on the CFD part, but all the preparation for CFD, even the post-processing of CFD. It involves innovative geometry and meshing technologies and thinks about workflow as well. On the acceleration side, that's partially workflow related, but also, of course, we're all on a GPU revolution, and our tools were very early on in that space as well. Accuracy is still mission critical. One of the reasons why CFD isn't even more important than it should be is because there just isn't the accuracy there for action in some cases. And a path to that is really through high fidelity. I'm going to talk about that a little bit today. And then finally, how is AI going to fit into all this? I mean, AI enablement, it will have a number of paths. Part of it will be in the way that the software is used, but part of it will also be in the way that we build models. All right, so a little bit on some of the tools that have come together. Some of you are probably familiar with Fidelity Pointwise. It's used pretty extensively in the aerospace industry. If you looked at Pointwise a number of years ago compared to Pointwise today, what you would be remarkably aware of is the level of automation that's been introduced to a tool like this. Many of the features that used to be much more manual are now being automated. And so the scripting that supports some of the work that you do in a tool like this is much shorter, much more functionally capable. That's the space of traditional grid generation at Cadence. In our high fidelity offerings, we actually use quite a different grid generation technology based on Voronoi diagrams. And I'm borrowing here from a slide from a presentation that you can go and see tomorrow, just to illustrate how complicated some of these calculations are getting. These are aeroacoustic calculations of a full wheel multi-stage turbofan engine where Honda and Cadence have collaborated to run these calcs and compare them against data. These calculations, the grid generation is based on Voronoi diagrams and a moving high fidelity solver called Charles. Now, the interesting thing about that particular grid generation technology is it doesn't have to stay isotropic. You can actually introduce anisotropy into the grid. We've had anisotropic grids forever. In this case, it's Voronoi diagrams introducing anisotropy. And that actually allowed a real hero calculation to take place earlier this year. There was a calculation of one of the configurations from the high lift workshop, but instead of running it in a wall modeled way, it was run wall resolved. So here you're actually adding viscous resolution to the boundary layer. So why would you do that? Well, the reason you do that is because there's an important transition happening on the slat. You can see it up there. If you don't capture that transition, the way that flow is set up for the rest of the wing is all wrong. And so capturing that slat transition was possible with wall resolved LES, and it could be done in about a billion cell mesh in about a day on quite a few GPUs. So that's an accessible calculation. Partly because of the way that CFD has come into Cadence with such a GPU thrust, and also all of the other drivers in the industry, has made Cadence adopt GPU computing very thoroughly. And so now we have our own version of a GPU accelerated hardware available on the cloud, or you can buy it on-prem. And the software technology stack, that middle layer of principled simulation, is not just in the CFD area. It'll span all the way from EDA, all the way through to molecular engineering flows, drug discovery. And so these three layers are finding their way through Cadence everywhere. All right, so how long does it take to do something interesting on a bunch of GPUs? The calculation on the left is a high lift calculation again, where you're looking at trying to predict the stall at high angle of attack, and you're doing it in a wall modeled setting. And nowadays, this is something like a 2-hour calculation for 20 convective time units. On the right, there's the turbofan calculation where you're going after the acoustics of the fan, not just the performance of the fan, but its acoustics. And that can run 10 revolutions rather in 50 minutes, which is enough to sort of do your post-processing of the sound, the noise signature. So this is really a game changer for these high fidelity methods. You can access parts of the operating envelope in a robust way that you just weren't able to historically. All right, so I think I've covered acceleration, accuracy, and automation. And so the last piece of the puzzle is AI. And there's been a lot of talk here at the conference about AI. What are we going to do with AI? I think anybody that develops software recognizes that AI is going to find its way into the way we program our codes. It's going to find its way into the way we use those codes as users through chatbots, agentic interactions with AI. But one of the interesting ways it will as well is it will find its way into the way we build reduced order models. There was a panel discussion yesterday that Cadence participated in along with ANSYS and a few other folks, where we looked at some of the offerings that are becoming available in this space. At Cadence, what we're focused on is a technology called geometric deep learning. So instead of thinking about a geometry as a parametric object, which is full of parameters, we're actually going to describe it as a geometry as a surface, a triangulation essentially that describes the nature of that surface. It turns out that these models can learn about those surfaces and then predict, as those surfaces change, how the responses will change as well, like the pressure distribution on those surfaces. So this was illustrated yesterday as a potential flow and the response, of course, is fast, really. The benefit here is you train the model on accurate data, and then you use the model to wander around inside that as kind of a magic interpolator. And that's what's illustrated here. you can actually position what's called a radon in a variety of different ways and evaluate to within a drag count how that will impact the drag of the system in a way that's got fast inference involved. Now, I think a lot of people have seen this sort of flow before. I want to show you a flow that you probably haven't seen, but it's still possible to stand up, and that's predicting aeroacoustics. So in this case, we did an internal experiment where we took the turbofan problem that I think I showed you earlier, at least something related. So this turbofan is the NASA SDT, and it has experimental noise associated with it, and it's already been fairly well optimized for its sound. But the outlet guide vanes are a big degree of freedom in a device like this. You can sweep them differently, and you can also give them slightly different angles. And so what we did was we actually used AI to learn from a few different simulations where we adjusted both the sweep angle and the and the angle of the blades, and we had AI predict the spectrum actually. So the output of the AI model was not the overall sound pressure level, but the actual details of the spectrum, right? And it turns out you can do this pretty well. It's a little bit hard to see, but these are a few of the different spectra that are predicted either by the full LES or the ML prediction. You're controlling the sound of this device by both reducing the tonal content of these tones and also reductions in the overall broadband sound content. And you can very quickly produce one of these maps that shows you what the operating space is like and where the optimum is. Normally, if you were going to do this, you would kind of populate it with some kind of tensor product grid and run, 64 calculations. In this case, with a handful of calculations, because the ML can pick out the modal content of what's going on, you can arrive at these maps fairly quickly. So what are these maps? You've got two regions that are kind of of interest, and they're also in contradiction. The red region is the region where you're keeping the adiabatic efficiency within about a percent of the peak efficiency. And the gray region is where the sound is within 1 dB of its quietest. And so these two regions are they're pulling apart from one another, but there's a nice robust region in the middle where the design can live. Getting to this place quickly is what AI can enable. And this illustrates that possibility. All right, so that's all I put together for you guys today. Come and visit us if you get a chance. We're just a booth over here. There's a lot of people that are here to talk about what we're doing in CFD, focused on automation, acceleration, accuracy, AI enablement. And if you have the time and you're a bit thirsty, please join us tonight. We're hosting an event. It'll run till about 5:30 to 7:30 in room 118. We've got not just our sales teams here, but there's a few R&D experts as well that really have been into the guts of the tools that we're writing and bringing together. Happy to have those conversations. Thank you. So, anybody have any tough questions for me? Yeah, sorry, go ahead.
I was going to ask, does the geometric deep learning method allow for topological changes, like surface genus change?
Yes, yeah. You've got to learn more, admittedly, because the mesh will change, but that's one of the nice features of that approach. It can certainly allow for topological changes. I mean, if the model were large enough, the topology could change dramatically.